Hey guys, good evening, and welcome back again to your Unacademy NEET English channel. I hope all of you are doing great, having a good time. My dear students, let me know quickly in the chats if all of you can hear me, if I'm perfectly audible, visible to every one of you. Let me know quickly in the chats with some fire emojis, all of you. If all of you can hear me, if I'm perfectly audible, visible, let me know quickly in the chats, people. Everyone means everyone. Good evening, and welcome back. Good evening and welcome back. All right, so people, as you all must be knowing, we have started these top 50 concepts of chemistry, right? Until now, you guys are done with 2 sessions. The first session I took, in which I discussed some 10 concepts. Yesterday, you discussed more concepts of organic chemistry. And today, we are going to discuss some more 10 very important questions. I mean, concepts with the questions as well. All right? So, are you all ready for the session now? Are you all ready for the session, people? Are you all ready for the session? I just want to know in the chats first. And at the same time, the handwritten PDF of these my sessions I keep on posting on my Telegram, right? If you are not the part of the Telegram channel yet, be the part of the Telegram channel as soon as possible. Okay? Be the part of the Telegram channel as soon as possible. The name of the Telegram channel is Wassim Bhat Chemistry Official. WASSIMBHAT Chemistry Official is the name of the Telegram channel. All right. Perfect. Should we start then? Should we start? Sir, stoichiometry क्यों नहीं पढ़ा है? Stoichiometry will be done too. Don't worry. I told you I'm going to give 3 sessions. Right? Today is the second session. Yeah. So quickly, let me know in the chats which part of the country you guys are watching me from. I just want to know which state you are from. I just want to know that. Yesterday's PDF also I'll be sharing in the Telegram today after the session. So tell me first of all in the chats. I want to know first which part of the country you guys are watching me from. The chats are stuck. Now they are moving. Okay. Karnataka, AP, Rajasthan, Tamil Nadu, AP. Telangana, Hyderabad, Kashmir. Gujarat, JK. Maharashtra, Rajasthan. Kerala. Okay. And. Telangana, Lucknow. Haryana. Nagaland, Pondicherry, UP, Bangalore. All right. Perfect, guys. Perfect. So Delhi also, that's great. Bihar also, nice, good. Perfect. Should we start then? All ready, people? Okay, so today also I will be discussing some 10 more important concepts from which questions are surely going to come when it comes to your NEET 2026 examination, people. Okay? All right. So let's get going. Let's get started with the first concept that I'll be discussing with you in the today's session. And the concept number 1 is the characteristics of your equilibrium constant, my dear students. Characteristics of your equilibrium constant. Many a times questions have been asked from this particular topic, characteristics of equilibrium constant. And you just have to remember few things, and I believe you can easily solve the questions which will be asked based on the characteristics of equilibrium constant. So without wasting further more time, let's get going. Let's get started with the characteristics of equilibrium constant. My dear students, few things I would want you guys to remember. And what are those things? Have a look. For example, you have got the reaction A in equilibrium with B. Let's say this is the reaction. For example, equilibrium constant of this particular reaction is, let's say, K. Let's say you took a reaction whose equilibrium constant is K. My dear students, first thing which you should remember from now onwards, whenever you reverse the reaction, so if I do one thing, if I reverse the same reaction, what happens to the equilibrium constant? Equilibrium constant gets inversed. What does that mean? That means if the equilibrium constant of this particular reaction was K, now the equilibrium constant of this reaction is going to be 1 divided by K. This is the first point which you should know. Whenever you reverse the reaction, equilibrium constant gets inversed. Point number 1. Point number 2. For example, you have got the reaction like this again. A gives B, whose equilibrium constant is K. My dear students, whenever you multiply this reaction by some number, whenever you multiply this particular reaction by some number, what happens to the equilibrium constant? If a reaction is multiplied by any number, that number goes to the power of equilibrium constant. What does that mean? That means if the equilibrium constant of this reaction is K, let's do one thing. Let's multiply this reaction by some number n. Let's multiply this reaction by some number n. It becomes n times A gives n times B, right? Now the equilibrium constant of this particular reaction is not going to be K, it will be K raised power n. So whenever you multiply a reaction by some number, that number goes to the power of equilibrium constant. Similarly, my dear students, for example, you have got the reaction A gives B, whose equilibrium constant is, for example, K1. One more reaction C gives D, whose equilibrium constant is, for example, K2. Now, for example, if you add these two reactions, the new reaction that you get, that's going to be A plus C gives B plus D. Now, what will be the equilibrium constant of this particular reaction? It will be the multiplication of these two. It's going to be K1 multiplied by K2. These are the three things which I want you guys to remember. And if you remember this, you're sorted. All right. So point number 1, whenever a reaction is reversed, equilibrium constant is inversed. When a reaction is multiplied by some number, that number goes to the power of equilibrium constant, right? Whenever you add some reactions, you have to multiply their equilibrium constants too. Now let's see what kind of questions can be framed from these 3 points which I gave you over here. Question number 1. A simple and basic question, guys. A simple and the basic question. Look at the question carefully. My dear students, if you look at the question carefully, we are given with a reaction whose equilibrium constant is given to us. The reaction is N2 plus 3 times H2. It gives what? It gives 2 times NH3. As far as the question is concerned, its equilibrium constant K is given to me as 49. Its equilibrium constant K is given to me as 49. Now, my dear students, I am supposed to calculate the equilibrium constant for this particular reaction. I'm supposed to calculate equilibrium constant for this particular reaction. Remember, the reaction whose equilibrium constant is to be calculated. The reaction whose equilibrium constant is to be calculated. You are supposed to make that reaction out of the reaction whose equilibrium constant is given. The reaction whose equilibrium constant needs to be calculated. The reaction whose equilibrium constant needs to be calculated. You are supposed to make that reaction from that particular reaction whose equilibrium constant is given. So basically, this is the reaction whose equilibrium constant is given. So I have to make this particular reaction from here. Now how? Use your brain a bit. Have a look. What I'll be doing? Let me just reverse this particular reaction. When I reverse this reaction, people, it becomes 2 times NH3, gives N2 plus 3 times H2. After reversing this reaction, equilibrium constant will be inversed. Now it's going to be 1 by 49, right? Now, my dear students, let me multiply this reaction by number 1 by 2. Let me multiply this reaction by 1 by 2. When I multiply this reaction with 1 by 2, what happens? 2 gets cancelled. I'll be left with NH3. It gives, this is going to be 1 by 2 times N2. And this is going to be 3 divided by 2 times H2. Since I multiplied this reaction with 1 by 2, this 1 by 2 will go to the power of Equilibrium constant. So it's going to be 1 by 49 raised power 1 by 2. The value comes out to be 1 by 7. Now look at this particular reaction carefully. Was I supposed to make this reaction only? Compare these two. I was supposed to make this reaction only. I made this reaction whose equilibrium constant came out to be 1 by 7. So the answer of this particular equation is nothing but 1 by 7. I believe this is clear to everyone, right? Question number 1. For example, let me try the second question too. Second question. Are you not going to take class on JK channel? Yes. My class is scheduled on JK channel on Sunday. Sunday, I'll be discussing complete class 12 physical chemistry there on JK channel. All right, leave that aside. Look here. Asha, by the way, all those people who do not know about the Telegram channel, this is the name of the Telegram channel. WASSIM BHAT 3. What was the name of the Telegram channel? Wassim Bhat Chemistry Official, yeah. Chemistry Official. This is the name of the Telegram channel on which I keep on sharing the notes, right? All right? Perfect. Let's move on. And let's try to solve this particular question as well. My dear students, 3 reactions are given to us and their equilibrium constants are K1, K2 and K3. 3 reactions are given to us. Their equilibrium constants are K1, K2 and K3. Yeah? Now, I'm sorry. I think I'm going to fall ill. Okay. 3 reactions are given. Their equilibrium constants are given to us, K1, K2 and K3. Now, what am I supposed to do? I'm supposed to calculate equilibrium constant for this particular reaction. So, my dear students, what am I supposed to do? I am supposed to make this reaction from these 3. Now, how will I make this reaction? Have a look. First of all, the reaction which I have to make in this reaction, your 2 times NH3 is on the left side. Among these reactions, here I can find 2 times NH3, but that's on right side. So reverse the first reaction. So I'm reversing the first reaction. It becomes 2 times NH3. It gives what? It gives N2 plus 3 times H2. Since you reverse this reaction, so equilibrium constant gets inversed. So now it's going to be 1 by K1. Right? At the same time, the reaction which you have to make in this particular reaction, 2 times NO is on the right side. Here among these reactions, here I can see 2 times NO, that's already on right side. So I'm going to do nothing with the second reaction. I'll keep it as such. N2 plus O2, it gives 2 times NO. And its equilibrium constant will remain as such, K2. Perfect. Right, people? Now at the same time, the reaction which I have to make, in that reaction you can see 3 times water is on the right side. Among these 3 reactions, I can see water here, but it's not 3 times water. So what am I supposed to do? I'm supposed to multiply this reaction first of all with 3. When I multiply this reaction with 3, it becomes K3 cube. Now, I'm going to write this reaction as such here. 3 times H2 plus 3 divided by 2 times O2, it gives 3 times water. Right? Its equilibrium constant came out to be K3 raised power 3. Perfect. Now, people, if you just add these 3 reactions, N2 gets cancelled out. 3 times H2 gets cancelled out. I am left with 2 times NH3 plus O2 plus 3 by 2 O2 makes it 5 by 2 O2. It gives what? It gives 2 times NO. And with 2 times NO, you get 3 times water. So this is the reaction which I was supposed to make. Compare these 2 reactions. This is the reaction which I was supposed to make. How did I make this reaction? When I added these 3. And when you add these 3 reactions, equilibrium constants are to be multiplied. So equilibrium constant of first reaction was 1 by K1 multiplied by. Second's equilibrium constant was K2. Third's equilibrium constant was K3 raised power 3. So this is the equilibrium constant for the reaction which I was supposed to calculate. So which option is matching here? People? It's going to be which one? Option number 1. I believe this is clear to everyone, right? Am I clear? Am I clear, people? Everyone in the chats once, quickly. This is going to be your homework question, which I believe you can easily solve based on the concept that I gave you right now, 2 minutes back. Yeah? Done and dusted? Right, people? Am I clear? Am I clear? Am I clear? Stereoisomerism will be also done. Just wait. Just wait. Do not spam. Whatever topics I had given you in the guest paper, that chemistry important topics one, all those topics I'll be covering. Don't worry. Is it clear, people? Let me know once in the chats. Quick, 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 quick. Say yes or no in the chats, quick. This sort of a question, I believe you can easily solve now, based on the same concept that I gave you. Yeah? All right. Let me move on then. Let me move on. My dear students, one direct question which will be theoretical, that will be asked to you. What will be that? You will be asked the examples of extensive and intensive properties. You'll be asked about the examples of extensive and intensive properties, right? First of all, you should know what are extensive properties. You should know what are intensive properties. If you look at the definition, okay, leave this definition aside. Let me make you understand what extensive and intensive properties are. See, for example, you have got an object. Let's say this is your object. This object is under observation right now. It is under investigation. This object, it's under investigation. And that something which is under investigation, what do you call that as? You call that as your system. Something which is under investigation, you call that as the system. Let's say mass of this object is m, volume is v, temperature is T. Let's say mass is m, volume is v, temperature is T. Okay, number one. For example, if I divide this object into two equal parts, I divided the same object into two equal parts. Now, for example, I am taking this part separately here. I'm just taking this part, right? Can you tell me what will be the mass of this object? It is going to be m by 2. Volume of this object, v by 2. But temperature of this object will be T only, right? It's pretty much simple, you know. See, look at this particular one. This object, right? Let's say the temperature of this marker is 25 degrees centigrade. If I cut this marker into two parts, right? The temperature of that part also will be 25 only. That's what I did over here. So first of all, this entire object was my system. Now, only this part is my system. Only this part is under investigation. So basically, am I changing the size of the system? Yes, I'm changing the size of the system. Initially, this whole object was under investigation. Now, only this smaller part is under investigation. So I can say I'm changing the size of the system. On changing the size of the system, is the mass of the system changing? Yes. Is the volume of the system changing? Yes. Is the temperature of the system changing? No. Let me tell you, those properties of the system whose value changes, on changing the size of the system, on changing the amount of substance present in the system, you call those as the extensive properties. So your mass and volume are extensive. Since temperature did not change on changing the size of the system, so temperature is intensive, right? Temperature is intensive. Perfect. So, extensive properties, these are the properties of the system whose value depends on the size of the system. Intensive properties, their values does not depend on the size of the system. I believe I'm clear with this, right? And my dear students, let me tell you, these are the examples which are frequently asked. Okay? These are the examples which are frequently asked. Now, here are 2 points which I would want to share with you. 2 points I would want to share with you. What is that? Have a look. My dear students, whenever you divide two extensive properties, the new property that arises, that's going to be intensive. What does that mean? For example, M stands for mass of the substance. Let's say V stands for volume of the substance. Mass is extensive. Volume is extensive. Mass divided by volume is called as density. Density will be intensive. Whenever you divide two extensive properties, the new property that comes into existence, right? That's going to be your intensive property. Perfect. Right? That's why you can see density I have written over here in intensive ones. Okay. Similarly, guys, one more thing. For example, A is an extensive property. Let's say A is an extensive property. Whenever you express this extensive property, either per unit mole or per unit mass or per unit volume, the new property that comes into existence, the new property that comes into existence, that's going to be intensive in nature. That's going to be intensive in nature. Remember this particular point as well. For example, my dear students, talk about entropy. Entropy is the example of extensive property. Entropy is the example of extensive property. Now, if I write entropy per unit mole, this is called as molar entropy. Molar entropy will be intensive in nature. Do you understand? Whenever an extensive property is expressed per unit mass, per unit mole, per unit volume, the new property that comes into existence, right? That's going to be your intensive. So remember, these are the examples of extensive and intensive properties, and frequently they are asked as the theoretical questions. I believe this is clear, right? I believe this is clear. And my dear students, if this is clear, let's have a look on one more topic, that is heat and work. That is heat and work. Two simple topics only, right? And I'll show you the types of the questions that can be framed here also. Now have a look what I'm going to say. Have a look what I'm going to say. This is our third concept. This is our concept number 3. Concept number 3. My dear students, first of all, few points which you have to remember. Point number 1. Whenever system absorbs heat, Q value is taken as positive. Whenever you see system absorbing heat, Q value is taken as positive. My dear students, whenever you see system releasing heat, Q value is taken as negative. These are the first two things which you have to remember. Whenever you see a system absorbing heat, Q value is taken as positive as per sign conventions. And whenever you see system releasing heat, Q value is taken as negative as per sign conventions. Right? Point number 1. Point number 2, my dear students. Point number 2. Whenever you see a gas undergoing expansion, whenever you see volume of the gas increasing, for example, this is the container and this is the piston. This is the piston here. The piston can go out, it can come inwards also, out also, inwards also. And this is the ideal gas, for example, in the container. If the piston goes out, volume of the container increases. That means the volume of the gas in the container, that also increases, which is what I call as expansion. Whenever there is expansion, whenever volume of the gas increases, whenever the gas undergoes expansion, we always say work is done. By the gas, by the system. Either you write gas or you write system. Similarly, whenever there is compression, work is done on the gas. These are two more things which you have to remember. Similarly, my dear students, how do we calculate this work? How do we calculate work? My dear students, there is one general expression with the help of which you can calculate work. How? Minus integral V1 to V2 P external multiplied by dV. This is a general expression by means of which you can calculate work. You just remember them for now. I'm not deriving these expressions. You just remember it. I'll show you how these are used in the questions. Okay? So first of all, this is the general expression to calculate work. Now. Sometimes in the question, they'll mention the process is reversible. Sometimes they'll mention the process is irreversible. Sometimes they'll mention the process reversible. Sometimes they'll mention the process irreversible. Right? My dear students, in reversible process, remember P gas and P external, they're almost equal. And in irreversible processes, P external is kept constant. What does that mean? You'll get the idea in some time. Okay? Sometimes they'll mention in the question the process is reversible. Sometimes they'll mention the process is irreversible. My dear students, how do we calculate work done in reversible process? Work done in reversible process will be integral V1 to V2. Instead of P external, we write P gas multiplied by dV. How do we calculate work done in irreversible processes? It is simply going to be minus P external into delta V. Minus P external into delta V. These are the two expressions which finally I want you guys to remember. And if you remember these expressions, you can solve the basic questions easily, which come from the term work. Okay? All right? So first of all, I believe this particular slide is clear to everyone. Whenever you see system absorbing heat, Q value positive, system releasing heat, Q value negative. During expansion, work is done by the system. W value is negative. When it comes to compression, work is done on the system, W value positive. Work, the general expression of work. Then you can classify process into two types, reversible and irreversible. This is how you calculate work done in reversible. This is how you calculate work done in irreversible, right? Now let's have a look what kind of questions can be framed. See, these are the frequently asked questions. My dear students. Identify in which of the process work is done by the system, work is done on the system. We have to identify that. Let's try to understand. For example, you have got the first reaction. The first question is 4 times NH3 gas plus 7 times O2 gas. It gives 4 times NO2 gas plus 6 times H2O gas. This is the reaction that's given to me. Now this reaction is happening at STP. That means pressure temperature has been kept constant. My dear students, whenever all the reactants and products are present in the gaseous phase, how do you check work is done by the system or on the system? You use ideal gas equation. And your ideal gas equation says that PV is equal to nRT. Since I have kept pressure and temperature constant, R is already constant, so volume is directly proportional to moles. If moles are increasing, volume is increasing. If moles are decreasing, volume will be decreasing, right? Now, my dear students, tell me on the reactant side, how many gaseous moles do we have? 7 plus 4, 11. On the product side, how many gaseous moles do we have? 6 plus 4, 10. So when this process is happening, are the gaseous moles increasing or decreasing? Gaseous moles are decreasing. When this process is happening, gaseous moles are decreasing. And if moles are decreasing, that means volume will be decreasing. Decrease in the volume is something which you call as compression. Whenever system undergoes compression, work is done on the system. So in the first case, work is done on the system, and you can say W value will be taken as positive. Done? But this is the concept which is used when all the reactants products are in gaseous phase. Concept number 2. Reaction number 2. My dear students, reaction number 2 says that carbon monoxide gas plus 2 times H2 gas. It gives what? It gives CH3OH liquid. Now, in order to check whether work is done by the system or on the system, are you going to use the ideal gas equation? No, you cannot use the ideal gas equation here. Why is that? Because in order to use the ideal gas equation, all the reactants products should be in gaseous phase. But here it's in liquid phase. Understood? So what do? You just answer the question as per state. What does that mean? See, this is gas, this is gas. So on reactant side, you have got gases. On product side, you have got liquid. On reactant side, you have got gases. On product side, you have got liquid. That means when this process is happening, gases are getting converted into liquid. When this process is happening, gases are getting converted into liquid. When gases are getting converted into liquid, what does that mean? That means the molecules are coming closer. If molecules are coming closer, volume of the system is decreasing. Decrease in the volume of the system is called as compression. And whenever there is compression, work is done on the system. W value is taken as positive. Right? This is something which I'll let you know in some time. Talk about the fourth one. Fourth one is H2O solid gives H2O gas. Tell me, is this the case of expansion or compression? I want you to tell me in the chats. Tell me in the chats quickly. Solid is getting converted into gas. So molecules are going far. Volume is increasing. Increase in the volume is what you call as expansion. Whenever there is expansion, work is done by the system. And whenever work is done by the system, W value is taken as negative. So here W is negative. Right? Now, for example, one more case I'm giving you. For example, you have got some X which is in solid phase. And this X is getting converted into liquid. So solid is getting converted into liquid. If solid is getting converted into liquid, again molecules are going far. This is the case of expansion. Work is done by the system. W value is taken as negative, right? But what if this X is H2O? What if this X is H2O? For example, you've got a scenario like this. H2O solid gives H2O liquid. What if this X is your water? My dear students, remember one thing. H2O solid is basically your ice. And due to the special cage-like structure of ice, volume of ice is more than that of volume of H2O liquid. Remember, volume of ice is more than that of what? Volume of H2O liquid. So when this process is happening, is the volume increasing or decreasing? Volume is decreasing. Decreasing the volume is what you call as compression. And whenever there is compression, work is done by the system or on the system? On the system, right? Work is done on the system. And whenever work is done on the system, W value is taken as positive. So here in this particular case, W value will be taken as positive. I believe this particular question is clear. Yeah? I believe this is clear to everyone. Perfect. Now, my dear students, one more question. Let me give that in the handwritten form. For example, the question is a system. System means ideal gas. A simple basic question I'm giving you. I just have to show you how to use the formula, nothing else, right? Okay, have a look. A system undergoes an expansion. From 10 raised power minus 3 meter cube to 10 raised power minus 1 meter cube against a constant external pressure. Against a constant external pressure of let's say 1 Newton against a constant pressure of 1 Newton per meter square. Let's say against a constant external pressure of 1 Newton per meter square. Calculate W in joules. A simple question I'm giving you. Why am I giving you this question? Because, my dear students, I want you to know whenever in the question they mention external pressure is constant. So you are going to consider the process irreversible. And in case of irreversible processes, how do you calculate work? Work is minus P external delta V, which is V2 minus V1, right? So W irreversible, now you can easily solve. P external is 1 Newton per meter square. V2 is 10 raised power minus 1. V1 is 10 raised power minus 3, right? So how do you solve this? This is minus. Take 10 raised power minus 3 common out of this. So it becomes 10 raised power minus 1 divided by 10 raised power minus 3 minus 1. I believe this calculation is understood, right? This calculation is understood, right? So when you take P external common, when you take 10 raised power minus 3 out, so it becomes 10 raised power minus 3 here. This becomes 10 power minus 3 divided by 10 power minus 3, which comes out B1. So this is going to be minus 10 raised power minus 3. This 10 raised power minus 3 goes up. It becomes 100. 100 minus 1 is 99. So the answer is going to be minus 99 into 10 raised power minus 3. Now, what are going to be the units? Since P external you have taken as per SI system, volume you have taken as per SI system, so W value will also come as per SI system, and the value of W as per SI system is nothing but joules, right? Yes. Now, my dear students, in the same question, if they say something like this, P is equal to 1 by V. If the question, they give something like this, P is equal to 1 by V, or P is equal to 5 by V, P is equal to 10 by V square, P is equal to 10 divided by this. Okay, if they give something like this, then take the process as reversible. And in reversible process, how do we calculate work? It is minus integral V1 to V2. It is P gas multiplied by dV. So what you have to do? Minus integral V1 to V2. P is given as 1 by V multiplied by dV. Then you have to integrate basically under the limits which are given, which would be given in the question. Okay, I believe these sort of questions you can easily solve from now onwards. This was our concept number 3. Now, my dear students, moving on to the concept number 4. Concept number 4. The questions are frequently asked from first law of thermodynamics. And you just have to remember one equation, that's it. What is that? Equation in chemistry is delta U is equal to Q plus W. But lot of students, they do mistakes in the sign conventions. They do mistakes in the unit conversions. So you have to remember certain things, then only I'll show you some questions. First of all, your result. I'm not going to derive this result, you know it already. If you do not know how it comes, then remember it. Delta U is equal to Q plus W. Delta U is equal to Q plus W. Delta U is internal energy change, Q is heat, W is work. Okay? Now, my dear students, what do you have to remember? First of all, what is the SI unit of energy? I'm talking about energy units. What is the SI unit of energy? Energy means heat and work, right? What is the SI unit of energy? That is Joule, right? That is Joule. Perfect. What are the other units of energy which we use in this chapter? If I ask you, what are the other units of energy which we use in this particular chapter? First of all, SI unit is Joule. Its CGS unit will be what? That's erg. The other units of energy which we use in this chapter. One of the unit is going to be atmosphere liter. One of the unit is going to be bar liter. One of the unit is going to be calories. These are the frequently used units of energy in this chapter. Remember, 1 ATM liter is equal to 101.3 joules. 1 bar liter is equal to 100 joules. And 1 ATM liter is equal to 24.2 calories. Remember these unit conversions. Remember these unit conversions. Okay? Remember these unit conversions. Now, my dear students, what kind of question can be framed from this particular equation? Many questions can be framed. Many questions can be framed. Many questions can be framed. Now, have a look on the first question. This is the first question, my dear students. Can you give it a try? Can you give it a try? I'm just asking you. Can you give it a try? Everyone. Will you be able to solve this question? Will you be able to solve this question? Say yes or no in the chats. It's okay. It's okay, people. It's okay. If you are not able to solve the question also, it's okay. I'm here to show you. Just I want the honest answers from you. I want the honest answers from you. Have a look. Okay, let me show it to you. As far as the question is concerned, a system expands from 5 liters to 10 liters. So initial volume of the gas is 5 liters. Final volume of the gas is 10 liters. Initial volume of the gas is 5 liters. Final volume of the gas is 10 liters. A system expands from 5 liters to 10 liters against a constant external pressure. As per the question, external pressure is kept constant. How much? That is 2 atm. Now you tell me, if external pressure is kept constant, the process is irreversible. If it absorbs 800 joules of heat, system is absorbing heat, so Q value is positive. System is absorbing heat, Q value is positive, right? Now, calculate delta U. We have to calculate delta U in joules. Perfect. Now, in order to calculate delta U, just use the first law. Delta U is equal to Q plus W. But this is W irreversible now. So I would say, let's calculate W first. How do I calculate W irreversible? W irreversible, there is a formula minus P external delta V, which is P2 minus V1. So W irreversible will be equal to minus. What is P external? That's 2 atm. What is V2? 10 liters. V1, 5 liters. So the value comes out to be minus 10. But what are the units of this W here? Here I have taken pressure in atm, volume in liter. So W units will be atm liter. But I don't need W in atm liter. Since I have to calculate delta U in joules, that means Q has to be in joules. W also has to be in joules. W also has to be in joules. I got W in atm liter. Now you know 1 atm liter is equal to 101.3 joules. So the value is going to be minus 1013 joules. This is the value of W. Now put the values and do it. Delta U in joules will be equal to Q. Q is given to me as I think 800 joules. All right. This value is already in joules. W is given as minus 1013 joules. When you solve this, the answer is going to be minus 213 joules. This is the value of delta U. Simple. Done and dusted. Okay, done and dusted. For example, there was one question asked in JEE Mains recently, a simple question, right? The question was something like this: delta U is equal to. Delta U is equal to. First option was given as delta U is equal to isochoric work. Delta U is equal to isothermal work. Delta U is equal to adiabatic work. And one is left, that is isobaric work. What do you think is the correct answer? I'm asking you. What do you think is the correct answer? I'm asking you. I'm asking you people. See, it's a pretty simple question. You know, first of all, delta U is equal to Q plus W. Delta U is equal to Q plus W. Now, when can delta U be equal to W? Delta U can be equal to W if Q is 0. If Q is 0, delta U comes out to be W. Now, Q is equal to 0 means which process? You call the process adiabatic process. So, I would say delta U is equal to W adiabatic. So, delta U is nothing but it's adiabatic work. Simple. Right? Yeah? Sir, can you take class in Tamil? Bro, I don't know Tamil. I can understand a bit of Tamil, but I cannot speak it. I cannot speak it. Okay. All right. One more question I'm giving you from first law of thermodynamics only. This also the asked question. The question is like this. During the compression of spring, during the compression of a spring, during compression of a spring, the work done is the work done is 10 kilojoules. The work done is 10 kilojoules. And 2 kilojoules escaped to the surroundings. 2 kilojoules escaped to the surroundings as heat. As heat. Calculate delta U in kilojoules. Can you tell me the answer of this question? Can you tell me the answer of this question? I think there is an earthquake. Wait. Guys, we'll have to end the class. Okay. Let's do only these 5 concepts today because sudden earthquake came from where I'm taking the session in Srinagar, and there are still like aftershocks. Okay, there are still some aftershocks happening. All right. So I was supposed to teach some 10 concepts. I discussed some 3 to 4. The remaining I'll do in part 3. Okay. The remaining I'll do in part 3. All right. All right, guys. You take care. See you. Bye bye.